Okay, so hopefully this is working. Apologies, there was some some of those questions I've done, as you probably, if you could see the timestamps, it was literally the middle of the night. So I apologize if there's been some mistakes anywhere. Okay, what I'm going to do is I'm literally going to take what I did with my class today at school and take the statistics and take the mechanics section and just go through the key bits. And we know that in the advanced information, they've said certain things, but I'm a little bit worried that there may be some bits that, like the integration in paper 1, which might be a part B, part C, part D, and you haven't covered. So I don't know whether you have, but especially the wordy bits. Now, statistics shouldn't take very long. There's only a few little bits that make sense there. So we'll do statistics first, and then we'll spend a bit of time on the mechanics, particularly on connected particles, just in case. All right, so for statistics, and I hope everyone can see this and it's clear, we have sampling. So when we've got sampling, let's think of some key words that you should know. So you should know that a census, so a census is everybody. This could be a part A or part B or something. And this measures every single member of a population. Now, from that population, you can always take out a sample. So you can take out a sample. And whereas there, we talk about sampling units and we talk about a sampling frame. So these are just words that you need to be able to relate. So the units are like the actual members of that population. And the sampling frame is like the list. So it could be everybody in your year, and it would be the registers that are your sampling frame. Now, in terms of sampling, if you do have anything, you've got random sampling. And this is every single person in the list has the same chance of being picked. You're picking out a part act. You've got a random generator, there shouldn't be any bias there. You've got systematic sampling, and that's when you take every single, every kth unit. So you take the population, so you could have 100 names and you want a sample of 10, so you do 100 divided by 10, and then you take every 10th person, right? So this is quick, but you have to have a sampling frame. So we say this is quick. This is accurate, but expensive, long to go check everybody. There's no bias here. So these are sort of random sampling. Now you also have, within random sampling, you also have stratified sampling. So stratified sampling, that's what represents groups of people. So that's where you proportion and you use ratio to even that out. Okay, then you've got non-random sampling. I am literally just talking at you, so hopefully you're obviously welcome to ask questions afterwards, but I can't actually see either of the screens of questions. So you've got quota sampling and you've got opportunity sampling. This is all the time I'm going to spend on this. I walked in the door a little while ago, so I didn't have time to prepare sort of pretty slides. So quota sampling is a bit like stratified sampling, but an interviewer kind of fills out who they want. So it's not random, it's potential bias, but say they want to get a certain number of one thing, or they're asking every 5th person that walks through the door of the supermarket. Opportunity sampling is the quota is filled by whoever's available. So whoever's willing to answer the questions. It's easy, it's cheap, it could be bias. Now, data can be split into qualitative and quantitative. So the quantitative is your numerical data, your qualitative is non-numerical. Now, the other thing that you have is the large data set. Now, what I'm going to do is I'm just going to grab which one I think you should use. There's like lots out there, but there's a summary which someone's done, which is not me, which one of a maths teacher's done, which I think is really good. So I will link it underneath the video later, but it's literally a one-page overview. Let me see if I can download it and put it up on a screen so you can see it. Right. So if I apologies, like I said, not as organized as I'd hoped to be this evening. So if I grab that, let's send it to myself. Okay. Okay, so this summary here of the large data set, and I'll link it, it's by SXP Maths, I think. So it's kind of the things that you need to know or could come up. Now, the things that I'm going to highlight within this is you need to recognize from the UK stations, what might what might hint you to things is you've got some coastal ones. So you've got some coastal ones, so things that are on the coast. And then you've got like, and generally, in the south as well. You've got 3 overseas ones. Let's do this. If I mention a few things about them, obviously Perth is in Australia. So you're swapping the summer and winter from where we are anywhere else. You've got Beijing, China, and you've got Jacksonville, Florida. And it's just the things that have come up in the past that have thrown people is what this means. So in your large data set, when they talk about rainfall, where you're measuring it in millimeters, if it says trace, you have to treat that as 0.025 millimeters, right? In any calculations. So if they say, what do we do with the trace data? You treat it as 0.25, sorry. And anything that says NA, you eliminate totally because it's not available data. The other thing that they've liked to test in the past, or they've used in some ways, is octas. When they talked about cloud cover, there was a discrete question, like a discrete distribution question one year, where they said, is it uniform? And you had to do 0, 1, 2, 3, 4, 5, 6, 7, 8, and recognize that it's 1/9 for each. So 0 means the sky is totally clear, 8 is totally overcast. Those are the things that I would highlight. I wouldn't worry too much, but it does say things, 1 knot is 1.15 miles per hour. When the great storms were, so they were only sort of 2 of them. I maybe just like glance at this sheet tomorrow morning before you go in. I got someone say, I thought trace was treated as 0. No, on all the mark schemes, and when we've gone to exact like conferences that they've done, Edexcel have done, they've advised us to use it as 0.025 or teach that to students. Okay. So I will upload this. I'll upload a link to it. It's, I think it's from, there you go, SXP Maths, but I will upload a link or, double check that it's happy to be on the Google Classroom. I can't imagine they would disagree, but we need to check these things. Okay, now the next bit is obviously representing data, right? So if we think about representing data, we can think about our mean, which know your calculator, right? So you've all got different calculators. Most of you should have either the Class Whiz or, I don't know which one it's called, the CG50. Make sure you know how to calculate and put all your data in, okay? The reason a lot of these questions are only 1 mark is because you're not expected to calculate anything manually. Calculator skills is actually part of the sort of syllabus now. Okay, so you've got your mean, and then you've also, let's just talk about, yeah, actually, let's do it, split it into mean, and then that's the location. And then if we think about how spread is done, you've got, with the mean, you get standard deviation. Now, standard deviation, so is sigma, and variance is its squared, and you get the formulas in your formula book. So in your formula book, you're given the formulas, but things to bear in mind, and I know you know this probably, but just to be on the safe side, if you get given a list of numbers, the sum of x squared is different from the sum of x all squared. So that weird E sign represents sum. Sum of x squared, so if I had 1, 2, 3, is 1 squared plus 2 squared plus 3 squared, whereas sum of x all squared is 1 plus 2 plus 3 all squared. Sorry, I'm talking really fast. I do appreciate that. If we've got a list of data, so with listed data, the other type of thing we use is obviously the median and the quartiles. So your lower quartile, or your Q1, is your number of numbers over 4. Your median, which is sometimes your Q2, is your n over 2. And your upper quartile, your Q3, is 3n over 4. Okay. If it's a decimal in a list, you always round up, right? And if it's a whole number, you find the midpoint with the next one. So round up if decimal, and whole number, find midpoint. Okay. The other thing that's come up in papers and students have been, well, a little bit unsure about is if something asks for the 32th percentile, all that means, and it might be written like this, so it wasn't an old spec question, but it's still in your specification. If you see that they want you to calculate P32, what they mean is 0.32 of n, and then you're going to use interpolation. Right, now, how I sort of do interpolations a little bit differently to the textbook. So if it's going to confuse you, you ignore everything I say. Okay, so if I was going to give you, I'm going to draw a table, like a really rough table. I don't know, 0 to 10, let's say 11 to 15, and 16 to 21. Now there's a gap, so obviously we fill them because normally it's continuous data. So that's actually 10.5. That's going to 15.5. So you shouldn't really have any gaps. So in your head, you're doing the 0.5, actually physically putting the 0.5 in. Let's say your frequencies are, let's make them like the numbers nice for me. 5, 10, and 25. Okay, and I want to know the 7th number. So I identify that the 7th number must be, and like I said, if you've got a strategy for this and it works, ignore what I'm saying, must be in this category because the first 5 numbers are in that first category. So you say, how many numbers into this group is it? So it's 2 numbers into the group. Out of a possible how many numbers? Out of 10. So that's your fraction. You adjust for how big the class width is. So 15.5 minus 10.5. So you adjust it by 5. And that's it. That's your fraction. So it'll be 10.5 plus how much into the group is it? So that's interpolation very quickly. If you've got another method, that's not a problem at all. Yes, I will be doing all the steps for each of the hypothesis testing as well. We're getting there. Let's just go through this initial bit first. I don't know, someone's just asked. So that's interpolation. We talked about interquartile range. No, we didn't. So I have lots of things. Interquartile range is your Q3 minus your Q1. Why is this good? So those are those random 1 markers. Remember that if the grade boundaries are lower, it also means the difference between each grades is also lower. So all those 1 markers matter. I have a student who was fantastic, but didn't like words And, you know, those just would always skip the 1 markers, and, you know, they got their grades, but it took a lot of convincing to write them down. So just do it. It's not difficult. Anyway, so why is the interquartile range good? It's because it ignores any outliers or extremes, or, you know, it depends on how the question is worded. So that's why you would use an interquartile range instead of a standard deviation. So your standard deviation is alongside your mean. It tells you how far away each of the numbers is away from the mean. So what's the spread of the numbers? However, if you've got extremes, it's going to throw your standard deviation out. So in that circumstance, sometimes using medians and interquartile ranges are better. And that's where like sort of coding comes in. So when you think about coding data, and you think about, you know, the mean and the standard deviation, the mean is affected by everything. So it's affected by adding and subtracting and by multiplying and dividing. However, so that's your mean. The standard deviation is only affected by multiplying and dividing. So it doesn't matter, because what the standard deviation tells you is how far away everything is from the mean. Now, if you add and subtract everything, everything shifts. So your standard deviation stays the same. However, when you times and divide, you stretch it. If you think of sort of graph stretching, so you have to change it like that. Right, we can represent things as cumulative frequency graphs, box plots, you know, so box plots, we should know, that's your lowest value, your Q1. They haven't really said much about this on the advanced information, but, you know, so then this would be your lower value and this would be your highest value. And then you represent your outliers with stars, and they're usually Q1 minus 1.5 interquartile range, for this is outliers. And they usually give you this formula. So they tell you what they want you to use. The cumulative frequency kind of represents the same way as a box plot. So you used to be able to see the curve as well. And then you've got histograms. And the only thing you need to know about histograms is that the frequency is proportional to the area. So you can look at the area and say it's the frequency is a factor. You can count squares, right? If you're ever asked, you don't have, unless you're asked, I don't tend to use frequency density, but that's going to be your frequency over your class width. So you might be asked to compare. If you're asked to compare, you're going to be asked to compare either the location, so the mean, all right, or how things are spread out, so your standard deviation and your interquartile range. Okay, so we've then got different types of distributions. So you've got your discrete distributions. So discrete, and that's where you're going to be able to draw yourself a table. So here is when discrete means it's 1, 2, 3, 4, it's not continuous. Like I said, like when we had that cloud cover question, I can't remember what year it was. But anyway, there's a cloud cover question. And in this case, they told you it was uniform. Now, uniform will have put alarm bells in your head to say 1/9, 1/9. Now, uniform means it's all the same. If you're asked to describe a distribution and every single thing is the same, you have to say it's a uniform discrete distribution to get your marks. Okay. So we've got, so for our discrete distributions, we've got something like this. You could have uniform version of it. We have a binomial distribution, which you all should know. And that's when you have X is binomial distribution N and P. So N is your number of trials. Okay, and what do we know? The number of trials, when they say what are the assumptions that have been made, these have to be fixed, right? They have to be independent. And when you do this in an exam question, you've got to always make it relevant to the, what's the word? So you've got to make it relevant to the questions. You've got to apply it. So if it's about, I don't know, the number of my brain has gone, the number of goals someone scores, you have to say, you know, or the number of games someone plays. It's a fixed number of games. Each time, blah, whatever name they use, plays the game, you know, each trial is independent, or each game is independent of the other. So you've got to just sort of use the words in the question when you do it, because we're not allowed to give you marks without context. Okay, P is probability, and this is the probability of success. And what we need to hear is we can only have binomial distribution when the probability of success is fixed to start with, and there are only two possibilities. So either you succeed or you don't. Either you throw a 6 or you don't. Okay, so there's only two possibilities, so two outcomes, a success and one minus that success probability-wise, which is not happening. In your calculators, PD is equal to, so the probability X equals to something. And CD, depending on which calculator you have, if you've got the CG50, you can put an upper and lower bound, but if you've got the class Wiz, it's less than or equal to. So be careful when you're doing greater than, you make sure you do your 1 minus. Is there anything else? You can do inverse. Oh yeah, and then you have inverse, which is like when you know the area and you're working backwards. You can also use the tables if you've learned how to in your formula books. So that's binomial. Let's have a look at the normal distribution, and then we'll look at the 3 types of hypothesis testing, and then look at mechanics. Okay, so the normal distribution. So normal distribution. I'm happy to put these scribbles up. They're not very useful, but if you think you'll remember what they were about, you're welcome to them. So if I take a normal distribution, it's a bell-shaped curve. Okay, so if you're asked to describe it, it's a bell-shaped curve. It's symmetrical. I probably can't spell. It's symmetrical. It has points of inflection over here and here. Okay, it should be symmetrical. This middle point represents your mean, and where your points of inflection are represent one standard deviation away from the mean. Okay. And what you need to know is you need to remember 68, 95, 99.7. So these are percentages. 68% is when you're within, so plus and minus, 1 standard deviation of the mean. This is when you're within 2 standard deviations, and this is within 3 standard deviations. Okay. Let's think normal distribution, your calculator, same thing. No, we never have PD. Okay, there might be a PD in your calculator, don't use it. The probability X equals something is always 0. So if they give you a 1-mark question and it's a normal distribution and it's X equaling something, it's because you've got this continuous data and it's this tiny, tiny little sliver. It's not worth anything. It's nothing. It's so small that we say it's 0. Okay. Please. So yeah, so that's that tiny sliver. Let's see what else. Finding probabilities, use your calculator. Oh, okay. And somebody asked me this, I think, on a question somewhere. They didn't really understand how the Z works. So all it is if you have your normal distribution, I would always sketch things. I think it's so much easier to see it. You have your mean here, and if you like, this is your X world of numbers. You're going to have another line, which is like your Z world. And your Z, so your X is normally distributed. So X is normally distributed, your mean and your sigma squared. You're in Z world, the normal distribution is always 0, 1. So you're trying to code every single number on the X line into a Z. So you're trying to make that mean 0. And the way you do that, so any point here or any point, so X1, say X2, and we're making it into a Z, we do x minus the mean over the standard deviation. If we sketch it, anything to the left, we expect to be negative, and anything this side, we expect to be positive when it's a z. And then we can, work certain things out. So you can use your inverse with your area, if you're given it, to work out your z if you're missing either the mean or the standard deviation. So if you're missing the mean or the standard deviation or both, you use if it's both, you'll get simultaneous equations. All right, the next thing is approximating. So we know that we are likely to have an approximating, I think they even said you're having an approximating binomial to normal. So remember, your binomial distribution is NP. Let's call it X, binomially distributed NP. And if we want to make it a normal, we're making it Y, and your mean is N times P. This is in your formula book as well. And your variance is NP1 minus P. Okay, I've not drawn that very nicely. So we can approximate it. And if it says, what are the conditions to approximate? N is large. I know that's not like definitive. It's just large. I mean, what does large mean? But you've got to sort of allow the fact that that's what they mean. So N is large and P is close to 0.5. Now, if they tell you to do a binomial approximation and this isn't the case, you still do it if the question asks you for it. Okay. The only thing is when you calculate things here, you have to do what we call continuity correct. So your continuity corrections, essentially, you're making your space bigger. What I mean by that is, say I have the probability in binomial world, in your discrete world, that x has to be bigger than 5, right? So that really means x is bigger than or equal to 6, because we don't want the 5. But what we want to do, so if we think of a number line, we're doing, starting at 6, making everything bigger. We want to make the bits that we're calculating bigger by 0.5. So actually, for y, which is my normal, I will be calculating bigger than or equal to, I mean, equal to doesn't really matter because there's no such thing in normal, but bigger than 5.5. So if I had, for example, let's pick numbers either side. So let's say we had x is bigger than 6, but less than or equal to 15. What I would first do is figure out for myself what that means in terms of equal to. So it's bigger than 6, but we don't want 6. So actually, it's bigger than or equal to 7, but less than or equal to 15. Right? So what we want to do is make our space bigger. So if at the moment we're going from 7 to 15, we're making it bigger by 0.5 either side. So actually we're going from 6.5 to 15.5. So my y that I would be calculating is between 6.5 and 15.5. So if you struggle with continuity corrections, that's the best way to do it. Okay, hypothesis testing. So if I give you a summary, and if you follow this format, you should be okay. You can occasionally be asked for definitions as well. So I think it was in either the specimen or the sample paper, they had one like sort of 3-mark question, just literally saying, what does a null hypothesis mean? And so on. So a null hypothesis, so your H0 is the assumption we assume, I think that's the right wording, we assume to be true. Or we could just say what we assume to be true. The alternative hypothesis, so your H1, is if what is true if the null hypothesis is not. is wrong, if you like. What is a significance level? So your significance level, which is normally, so significance level, so that's going to be some percentage, is your given, what's the word, threshold of likeliness. So the given amount that we think it's going to be likely, likeliness, yeah, sorry, Li. You can tell I'm a math and physicist, I really can't spell. Right, one-tailed test means you're only looking at one side, and a two-tailed test, and so here you just take your significance level, so say this is alpha percent. Your one-tailed test, you look at the total alpha. Your two-tailed test, you split that in two. So you half your significance. Okay. Right, so let's take, there's going to be 1, 2, 3 different types. So you have, for correlation, let me think the best way to lay this out. Okay, so let's do correlation testing. We have correlation, we've got binomial, and then we'll do the sample mean separately, because it's a little bit different when we've got the normal. So if we take correlation, if we take binomial and correlation testing first, right? With correlation testing, your H0 is always rho equals 0. Now, if yours looked like a P, like mine does there, you're going to get the marks. So don't spend so long. Yeah, I know I went really fast. The significance level is essentially the given threshold of likeliness. This is recorded, it's on YouTube, so you can go back over different things. Okay. All right. So H0 rho equals 0. So you can write it like that. And H1 will be one of 3 things. Either it's bigger than 0, either it's less than 0, or it's not 0. So you have to read the question, look for words increase, decrease, just change, right? With binomial, if we say X is binomially distributed, NP, and I'm going to call my P in this case K, right? Yeah. So then your H0 is always P equals K. So it's always given, and you always give it in context with the question. It's always been the question. And H1 is therefore P is bigger than K, less than K, or not K. So these over here, so if we have a look, these two are a one-tailed test, whereas this one is a two-tailed test, right? So you've got, sorry. So you've got one tail. So these are one-tailed, and this is going to give you your two-tail. Can't really see that, can you? Two-tail. Okay. So then with the correlation is the one that's super easy. You get your formula book and you compare your R with the table. Okay, so if we have a look at the formula book, I'll show you that in a second. And if your R is more positive or more negative, so in the table, it's only giving you positive numbers. If you get a negative correlation and you're doing less than, you just make that number negative that's in your tables. So if your R is more positive or more negative, so it's more extreme, that means you can reject H0. Remember the context of the question, it will change for each question. So you say there is enough evidence to reject H0, so Mr. Blah blah is right. The correlation has increased. Okay, between whatever it is. If your R is less positive or less negative, you write there is not enough evidence to reject H0. So therefore, the correlation is, and again, context of the question. With binomial, what you do is you assume your H0 is correct. So you calculate your binomial using this. Now in the question, it might say 11 people came in. Now, if your H1 is greater than, then when you work it out, you're going to just make it greater than. So you're working out the probability X is greater than or equal to whatever the value is, or less than or equal to, right? So you're always going into the extremes. Now, if it's two-tailed, sorry, you have to think if, for example, the mean is 7 and you're testing the number 3, right? Then you actually want, if you take 7 and go greater than, you're going to get a big number. That's not going to be, an extreme where you can reject, so not so small. So you're going to look at the less than. So it's just the significance level that gets split. Okay, so anyway, we work out, and if your probability is less than your significance level, you reject H0, right? So if P is less than, and if you reject H0, and then you do your context, and if P is greater than your significance, you say there is no evidence to reject H0. Now, you should also look at critical values. I don't think I've done a question where I've looked at them, but have a look through. If you don't remember critical values, I suggest you just read through. You've probably got the Pearson books. There's a good example in there, but that's where you're using the tables as well. So before we move on, I'm just going to quickly show you the tables for correlation. All right, I'm going to save that. If I grab my formula books, which are here somewhere. Right, so here we go. So we've got our correlation, and what you look at is you look for your sample size. You're looking at this side, so it's in your formula book on page, I'm not sure, it's towards the back, and you find 5%, for example, and you take 0.7293. Now, if you're looking at the negative one, you're going to take minus, you just make the value minus. You look at your number and you say, is it more positive or is it more negative? So that's where you use that. In your formula book, you also get your binomial tables. Now, I know you have calculators, but sometimes these are easier to use. And if you're looking for critical regions, so if we're looking for critical regions, what we can do here is, for example, we were looking for, I don't know, let's take something, so n equals 8, and we were looking for, the P was 0.2, and we were looking for the critical region at 5%. So we're saying it's a two-tailed test, which is when we normally end up using critical regions, and we're looking at 5%. So we split that 5%. So it's going to be 2.5% on the bottom, 2.5% on the top. And you literally go down your first number, you're going to say, well, this is already, oh, okay, maybe I chose the wrong numbers, but anyway, this is already bigger than 2.5%. So X would have to be 0 to be in your, because if you times that by 100, it's bigger than 2.5%. So to be in your critical region, and on the opposite end, you're looking for 90. So you're doing 100 minus 2%, so 97.5. So everything bigger than 4, you would reject. Okay, I chose too small a value. Typically, you'd use one of them down here. But hopefully that gives you a sense of it. When you do a question, hopefully it makes sense. Right, so those are your correlations. Sorry, went off on a tangent, didn't mean to confuse you. Right, let's have a look at normal. So the last type, and the last bit we're going to look at before I look at mechanics, is your normal testing. Now, more than likely, they've said normal distribution. This is, you're going to have to test a mean. So when you do normal, you're always testing the sample mean, right? Now, when we represent the sample mean, we represent it with an X bar. And we say it's normally distributed, the mean sigma squared over n. So this is what we have instead of our variance. And remember, when we put it into our calculator, you don't forget to square root it. And this n here is your sample size. Okay. Now for this, your H naught is always your mean equals, so if I say X is normally distributed sigma, so this is your population, it's distributed like this. This X bar is your sample mean. I'm going to change this to, I'm going to say this is M. So your H naught is always mu equals M. And your H1 can be mu is bigger than M, mu is less than M, and mu is not M. And you always assume that what you have in this distribution is true. And you find the probability that X bar is bigger than whatever value it gives you that they think the mean is changed to, or less than. And again, if your probability is less than your significance level, you reject H naught. And if it's greater than, not enough evidence to reject. So it works in the same way, but the enough evidence to reject. But the important thing is this, which again in your formula book, you're given. So if you go blank, flick through your formula book, and in your formula book underneath, so let's go all the way back, further maths. Okay, where are we? Still further maths, here we go. Under sampling distributions, it's not given explicitly, but you're given sigma over root n when they're talking about a random sample from n observations. So if you go blank, it may correlate in your head. This is essentially showing you if it's got a sample and you're converting, your x minus your mu over sigma for your z, this is how you do it. Okay, so that's stats very, very quickly. I've put some questions up. They might be err on the side of being less wordy. I suggest you look at some of the questions where you have within binomial, you have things like given. So, and we didn't really look at probability. Okay, you know what? I'm going to do one last sheet on probability. I feel like I should. We'll probably go on a bit longer than I planned to, but let me just go through as we were talking about probability and maybe correlation as well. So let me just go back to correlation. I do not know what my Apple Pencil is doing. Okay, sorry, give me 2 secs. Okay, correlation. So with correlation, we have our PMCC, so our product moment correlation coefficient. It's between -1 and 1. Okay, -1. I'm having technology fail. 2 seconds, I got a spare pen. This works better. Okay. Oh, I'm sorry, guys. Give me 2 minutes while I. Okay, so it measures your strength of your correlation. So your correlation is going to measure the strength of your correlation. And what it's going to say to you is if you have, it's closer to -1, it's got super, super strong negative correlation. It's perfect negative if it's -1. And if it's +1, it's perfect positive. So I'm just resetting my iPad. It's perfect negative. When you decide if you can if you can use a regression line, you can use a regression line if your correlation is strong. So if you've got strong correlation, you can use a regression line. If you don't have strong correlation, then you can't use a regression line. So let's try this now. So a line of best fit, I will otherwise, here we go. All right, perfect. Right, so the line of best fit is a straight line. So like your y equals mx plus c. Let's just make this so I can, that's better. All right, so your line of best fit is y equals, and in statistics, for some reason, they don't use mx and c, they use a and bx. Your a represents, is like your plus c. So it's when x equals 0. But in context, it's always your initial. And this will always represent how much y changes when x changes by 1. Changes by 1 blah, so whatever your unit is. Okay? You have interpolation and you have extrapolation. Now, these are quite important. Now, if you have a set of data, and if you're finding a point way outside that set of data, you're extrapolating, and that is less reliable, or it's unreliable, and it's not advised. Now, if it's within your data, it's interpolation, which is what you've done. When you interpolate and we find the median or the percentiles, and this is more reliable. So we prefer it to be within our data or not far from it. We know we're going to have coding. So as I've said to you with the questions, I suspect it's probably an exponential. So make sure you know your 2 exponential, transformations from AS. So with this one, if you take log of both sides, this side is the same as adding. And then the x can also come down. So x log b, or it could be natural log and learn, it depends on the question. Now, if we take our y equals a plus bx, we can say that represents your plus c, your y-intercept, and log b represents your gradient in this case. But you could also have a x to the n. And so in this case here, your graph plotted would be log y against log b. Against x. Sorry, normally not log b. What have I done here? Sorry, clearly rushing. Let me fix this before someone writes something down. X log b, and we've got bx. So your x matches up with your x, so your gradient is log b. So you've got log y against x. In this one here, which is what you're going to have log a plus n log x. And here, your graph is log x against log y. And you match it up. All right, so just to make that super clear, y equals ab to the power of x. That's when you're going to have a log y against an x graph. Your gradient is represented by log b, and your y-intercept by log a. Whereas in this case, you've got a log y graph against a log x graph, and your gradient of n, so if you have y equals a plus bx, right? So x and that match. So your gradient of b is your n, is the number that will go here, and your a and your log a match up together. So your y-intercept with log a. Okay. Probability. Right, probability. Probabilities always between 0 and 1. So always between 0 and 1. You will have Venn diagrams. Middle bit is and, probability A and B. Everything else, if you have everything, it's or. So this is A, so this is A and B, okay, let's do that. A and B, because I'm not going to put numbers in, and that's A or B. Sorry, it's very scribbled. Definitions, mutually exclusive. Two things that can never, ever, ever, ever happen at the same time. So A and B is 0. So I don't know, it being Monday and Thursday in this room at the same time is not going to happen. They're two mutually exclusive events. Independent, now independent events can happen at the same time, but to find out the probability, you times them. So you can only statistically prove it. In terms of an example, I don't know, me wearing a grey dress and you wearing yellow socks, they could happen on the same day, but I don't phone you up to check, and they're not dependent on each other, but they could feasibly happen at the same time. Conditional probability, that line represents the word given. So A given B is you're making your world smaller. You only care about the thing that's happened. So the thing that's happened is B, and you want to know the probability within that A happens. So if in terms of a Venn diagram, it's very easy to see. If you have, we say A, B, C, and we want the probability of A given C, it means what we do is we don't care about any other number except for what's inside C. And then we say, put that on the bottom. And then out of that, how much is A? It'll be whatever is in this bit and this bit, and that would go on the top. So given just means you're making your world smaller. Okay, now I'm happy that I've covered everything, or in some sort of way. So I'm going to move on to mechanics. I hope that's kind of made some sense. I haven't really looked at any of the comments. But for mechanics, or in terms of anything else, I'm happy to. I've got my work solutions, but as you probably realized, where some of you found some mistakes, it wasn't checked, which is why I was hesitant to put it up. I think enough of you have worked through the questions, and I've corrected the stuff that wasn't totally right that I did in the middle of the night. So I will make sure I put those up. I'm not sure how useful they'll be. You've got all the work solutions online, but I'll put them up today as soon as we finish this and I've had some dinner. Okay, so mechanics. Let's have a look at mechanics. So mechanics. Now, I'm not going to go through everything. I'm going to make the assumption, and if it's a wrong assumption, you need to make sure you go back and have a look, that some of your basic kinematics you're happy with. So you're given the SUVAT equations. SUVAT is just, you know, the initial letters. We haven't, in the advanced material, it doesn't really talk about graphs, but if I were you, I would just make sure you're happy with your speed time graphs, you know, and each of your different types of graphs. So if we think, if we have, because we're told we've got vectors, so let's have a look. If we've got constant speed, okay, so constant speed, V equals 0. So that's like speed equals, you know, the distance is speed times time. You know, you can change your units if you have to, like you do at GCSE. But essentially, if I was to draw a graph, if I've got constant speed, then I've just got a straight line. If this is my V and this is my T and this is my time. So constant velocity, yeah, and speed, you'd write speed there and it wouldn't have a direction, so you wouldn't go negative. Now your distance traveled is always your area underneath the line. And your acceleration is the gradient of the line. Now there you go, perfectly straight line, hopefully. So there is no, so there's no acceleration. In terms of thinking of things in sort of vector world, when we've got constant speed, because we've been told there might be something with kinematics and vectors, if you want to represent, you know, the position vector, we normally represent it with an R. So where something is at a given moment, it's where it started plus what its speed is. So whatever this constant speed is, sorry, they shouldn't say V is 0, they should say A is 0. Okay, whatever this constant speed is, times the amount of time. And I'm going to underline them. You don't have to underline your vectors, but these are the things that you expect to be vectors that you substitute in. Then if you've got constant acceleration, that's where these formulas come into play. So this is when you have constant, I can't spell, so constant speed or velocity. This one is constant, it's constant, you can tell it's been a long day. Acceleration, I've been talking way too much. Okay, constant acceleration. Though this is before you don't use variable acceleration here, there's no differentiating, there's no spar. This is, the question will state constant acceleration, and everywhere in your question, you will have a t. And again, the area under a graph gives you the distance traveled, and the gradient at any point gives you the acceleration. And it's always going to be straight lines because it's not variable. Right, so in vector world, which one of these, because we will have vectors, are vectors. So your V is a vector, your U is a vector, your A is a vector. You're not going to have your T. Here, we don't generally represent things like this. You would represent it as R. You'd say, where does R start? So what's my initial position at midday when something starts? Plus U, which is a vector, T, plus a half. Your A is a vector, T squared. So if you were representing a position vector or trying to find one, that's what you could use. So in that context, variable acceleration. So variable acceleration. So the question I gave you was a little bit tricky just because it was the algebra was a bit weird. You had to take out a factor to get a square, but think of var, or, you know, S is X as well. You differentiate down and you integrate up. So to go from displacement to velocity, you differentiate. From velocity to acceleration, you differentiate, and the other way you integrate. When you integrate, don't forget your plus C, because that's going to essentially give you your initial point in some cases. Okay. Right, so with vectors, because they've told us vectors, and if I looked back at all the questions, and you get a lot of things regarding, you know, northeast, southwest, or different directions. So if you see something that says something is moving, so like the question in the example, in a direction, that means it's moving at some lambda that direction. So I can't remember what the example was, but say it was I plus 4j, it says it's moving at lambda I 1/4. So you end up with simultaneous equations. Write them at columns if you need to, right? Now here, if something is northeast, so I would almost learn a few things. Okay, so we're going to have, so if something is at, let's do this. So here, if something is northeast off a value, you could almost think of it in the same way you do with lambda. So northeast and southwest are all along this line, y equals x. So you could just say it's when lambda 1, 1. So when your I component equals your j component, because this is the line y equals x, if it was an xy axis. If, however, you had, you know, northwest and southeast, this is the line of, let's make sure it goes through axes. So you won't get anything in between that. So this is the line when you have y equals minus x, right? So in this case, you're going to have lambda is, so lambda, so here, you know that if, for example, you have, I don't know, minus 2, your y coordinate here is 2, right? Because it's still 1 to 1. So what you will have here is you will have minus 1 and 1. And you would do it in exactly the same way. So that's one way to think about it. if you wanted to. So essentially your minus your I component equals your J component. So if you want to think of it like that, you'd say here you make your I equal to your J. Here you make your I equal to your J. Here you make your I equal to negative J. And here I equals negative J, or vice versa. All right, it doesn't matter because it means the same thing. Right. I think that on kinematics and stuff, I would do some questions and I'd make sure you know any of your modeling assumptions about particles and so on, but you should be okay if you've done the questions that I've listed. I don't think it can be asked in that many different ways. We then have projectiles, and I think I've done enough examples of them where you've got horizontal and vertical. Horizontal motion, A is always 0, vertical A is minus G, right? If you're asked to find the speed of anything, right, the speed is the magnitude. So you have to find the horizontal and the vertical component and Pythagoras it, and that bit would be your speed. And then you also need a direction, so you'd use tan minus 1 or for your direction. And let's think. I think that's it on there. So let's look at forces. Actually, before we do forces, let's look at our modeling, like our assumptions. So if you have a light string, what are you assuming? So light ends in the letter T. This tells you that the tension is equal throughout the whole string, right? Because you're considering all as one throughout the whole string. So this happens mainly with like pulleys. If you have, so with staying with a string, if we have an inextensible string, this tells us the acceleration of both particles attached to it is the same. The smooth pulley, if we're talking about connected particles, the tension on either side, so the difference either side of the pulley is the same. So if you get asked smooth pulley and light string in the same thing, if there's only one of them, you would just say, you know, light string, the tensions are the same. Smooth pulley, but if you had both of them, one is because the tension is equal over the whole string, and one's telling you either side of the string, the tension on either side of the pulley, sorry, is the same, not to do with the string. Okay, I'm trying to think if there's any others. Oh, sometimes they ask you about a particle and what better assumptions you can make. So when we have a particle, when we say particle, we ignore air resistance, and we also ignore any effect from the shape. So like any rotational effect from the shape. So whether it's like a rugby ball or a golf ball, it would move differently. The rod is rigid, so it doesn't bend. That's another one of your assumptions you may have. Sorry, I'm looking down at questions, trying to see where they've asked for assumptions. Okay, so now if we think about forces, we can have things which are in equilibrium. So if things are in equilibrium, so let's think about forces. Sorry, I'm feeling like I'm talking lots and I'm not looking at any questions. So please make sure you put them, because I'll probably miss everything here. So make sure you put them underneath the YouTube channel or underneath one of the videos. And later this evening, I promise I'll go through them. So if something is in equilibrium, it's static or it's at rest. Okay. And essentially it means left equals right, up equals down, you know, all the bits, you know, the slope, up the slope equals down the slope. Sometimes you're told it's on the point of slipping, up or down, and that tells you which way your friction goes. Now, somebody earlier, when they were looking at my examples, said on their diagram, I should instantly put FR equals mu R. technically they're correct. You won't lose marks for not stating it, but in your exam papers, you see equilibrium, you see any of those questions, you can write it. You're not going to lose any marks. So there's no marks allocated for stating anything, but there might be a part B to say something about the friction on that note. If you see the word resultant, so if we're thinking in vector form or equilibrium, so resultant means the result, you just add them up. If we're now in equilibrium, they all equal 0, okay? We know that F equals ma, so this is static. So if you remember in your textbook and on the information, you've got statics and you've got dynamics. Static essentially means it's not moving. It's in equilibrium, it's staying the same, right? And F equals ma, we're now moving into dynamics. So something is moving because you've got an acceleration, right? So whenever you do this, you resolve. Now your particle will not be jumping off the paper, like jumping off the, I don't know, slope. It'll be moving up and down the slope. So so jump like, this way off the slope, perpendicular to the slope, you can resolve as if it was equilibrium. And then use F equals ma along the slope. Friction. So friction is always opposite to the direction of motion. Direction of motion, right? If we're in a static world, FR is less than or equal to mu R. So that's your technical term. So if it's static, if it's in equilibrium, then F equals mu R, right? On a slope, generally, so when we're moving, mg, so if we think about any slope, we've got our m, g going down. We've always got our r going up. We've always got our theta, our angle there. And so this always is that angle there. And to go from the top to the bottom, you go this way and this way. So you're going along and down. So that's why your arrows are in this direction. This is mg sine theta. Going down the slope will always be sine theta. And this is mg cos theta, which is part of your resultant. Now, if mg sine theta is bigger than your friction, then it's going to move because your force going down is bigger than what's trying to stop it going. But if your mg sine theta is less than, so this was an exam question, oh God, a while ago, and people said it went the other way. It doesn't go the other way, it just doesn't move, right? So if your mg sine theta is less than, so it's not strong enough, the friction stops it moving. It doesn't make it move in any other kind of way. Okay. Right. Force diagrams, or like forces and, resolving. We're happy to resolve sine and cos. You have connected particles. So I did not put any questions in my sort of mechanics questions I went through on connected particles, mainly because they didn't explicitly say it, whereas on the AS paper they did. Now, having done some exams and having seen the news of lots of other exam boards having not done things, as great, I don't think you should ignore it. I don't think you should not study it at all. You've obviously studied it for school, but I think you should think about connected particles. It works in the same way. So if we have things on a horizontal, we've got, for example, a car and a truck, they're connected. The tension is always towards the middle. Say it's moving in this direction, you may have some resistive forces, and you may have a big force going forwards, right? When it's going this way, so when it's moving along, this is called tension. If this was to brake, so if the car in the front brakes and the forces flip round and go the other way, the ones here, they become thrust. So they become thrust, and that's just something to bear in mind. And here, all we do is we can think about the whole system where we do F equals MA, and the T's will cancel out, and then we can work out whatever we're missing. We can think of just, let's call this a car and a truck, car and something that's pulling, I don't know. Why is my brain gone blank? Sorry. I don't know what it normally pulls. I'm just going to put a box. Right. So it's normally a trailer. That's it. That's the word. Sorry. I was looking for the word trailer. We can think of the whole system. We can think of just the car, or we can think of just the trailer. But the thing to remember is the A is the same for each of those connected particles. So that's the first type, which is probably the most straightforward because you've got no slopes or anything like that. You then, and nobody likes these, you have lifts. And I don't know why lifts seem to always get a bad rep, because they're actually not difficult to think about. So if you have a lift, you've got to read the question. It will tell you what direction it's going. But regardless, if the lift has whatever the lift's mass is, it's got mg going down, right? And it's going to have some tension pulling it up. Now, say you've got somebody in that lift, they will have their own weight, so their own mg of sorts, and they will have their own sort of reaction force acting on them as well, right? And we can think of them all separately. So if we think about it, in terms of the lift, you've got your reaction force. You wouldn't draw this as a force diagram. I'm just trying to show you what's there. And you have to know whether it's going up or down, because you always resolve in the direction of acceleration. So here, if I was going to take boxes, we can have boxes. So there's been questions with boxes, A and B, for example, in a boxes in a lift. You've got your tension going up, and you're going to go down. You're going to have everything. So you've got, I don't know, the mass of A plus the mass of B plus M. Let's just say that's the lift multiplied by G. And then in between those boxes, you're going to have forces on each other. But you don't consider that when you're considering the lift as a whole. I have some lift questions. Let me make a note. And if I forget and anyone wants them, I've got some worked examples. Let me know and I'll upload those as well. So that's lifts. Pulleys. So if we've got a pulley, you've got mg, and let's say, I don't know, this is a big mg. Tension is always towards the pulley when you're calculating it. You take the heavier one, if they don't tell you, goes down. The other one goes up. And then you do F equals ma in the direction of acceleration. So you split it, and you're going to think of each of them. If they ask you for the equation of motion, so equation of motion for A, they're asking you for F equals ma. So they're asking you for mg minus t equals ma. And in this one, your equation of motion would be t minus mg equals ma. And then you solve them simultaneously. You do have simultaneous button in your calculator, which you can do. So that's like a nice straightforward pulley. If they ask you for the tension, so this is the tension on the strings, and if they ask you for to work out sort of the tension on the pulley, what you do is you essentially say, well, technically, and I don't draw it in when I do the diagram for the calculations, tension acts both ways. So you've got your particle and you've got your pulley. So for the pulley, if it's just straight down like that, it's just 2t. So whatever your tension is, you double it. So if you like, your format is always your equations of motion, which is just F equals ma for each of them. Solve simultaneously, And then your next part, you might have to use suvat. So they might be like, it hits the ground, it doesn't. Like I said, I don't expect there to be a big question on this, but I could be wrong. So make sure you recognize these, okay? You could have pulleys on slopes, but they work in resolving in the same way. And then you have moments, which hopefully I've given you enough questions of. There's a few ladders questions. I think I'll try find them, but I'm pretty sure I did them either on TikTok or on YouTube absolutely ages ago. But you have your ladder, which I think I've done a lot of questions for, and they always work in the same way. And I really like ladder questions because I think they're really easy. So you've got mg, you're always going to have an r there, you're always going to have your friction there. I know mu r there, you're always going to have a reaction this way, and you might have friction here as well. So I'm going to call that mu2 r2. N, sorry, it's not N, it's N, mu2n. Okay. And you always do, for any ladder question, you do exactly the same thing. You do you do up equals down, left equals right, and you take moments at A. And it should always work. So if it's uniform, the weight's in the middle. If it's non-uniform, I think there's an example when it's non-uniform, it doesn't act on the center. If something is on the point of tilting, it means whatever the point of tilting is, so normally that happens with, like a rigid body like that. So say you have, I don't know, I should have done it. So a reaction at A, a reaction at B, and you've got mg here, and say you've got the weight of the rod there. Okay, so if this said it was tilting and about A, so that means the A, it's tilting on A. So it means the B is about to come off. So here is where it's about to come up. So if it's tilting about A, the other place, so RB in this case would be 0. All right, so where it is at B is 0. Okay, so you've got a ladder. You could have a rod, so you can have something like this, like it's drawn like that. And you may have a string like that. Okay, so tension always up. And say the weight is acting on the rod here. What you will have in this case is you will have over here, you will have a horizontal and a vertical component of the reaction. And you work them out separately, but it works in the same way. So all you're going to do is obviously you resolve this T, wherever your theta is, T sine theta, T cos theta, and you're going to do up equals down, left equals right, and you will take moments from your equivalent of A. So, normally we have AB, even if this is not called A, but you take moments there. And then the last type that you might get with moments is when you've got like a rod like so. No, let's try to draw them in the same color. Not that I think anyone is going to understand this afterwards, but you never know. One of you might use them. Right, so if you've got something like this, and this will have, it's leaning against, so you've got a rod like this, you're going to have your XY component over here of your contact component. You'll have your weight, and you might have something like this, some force here. This is like the cylinder one where it was sitting on something which would be at right angles. And again, you do the same thing, up equals down, left equals right, moments at A. Okay, so you resolve up and down, you take moments at A. General rules, your weight going downwards, if this is your theta, it's always going to be your weight, so your mg, times by A. So this is always going to be your perpendicular bit, cos theta, and your n is typically going to be double that length if it's uniform and sine theta. And then you can work out all your other forces. But if you need some rules to help you remember. Okay, I think I've talked continuously for an hour and a half. Anyone who stayed, well done. I hope that was a little bit useful, or it's useful to somebody going forwards. Ask me questions. I will put up the worked mechanics solutions. I will make sure, I think by now enough of you have worked through them, so I know that they're correct. There was that 6B where actually I was doing the original question and I got it confused because I've had to change the questions quite a lot in order not for the examples not to make me take them down. So yeah, I hope it's been useful, and yeah, good luck. You guys will be fine. It's going to be okay. No matter what happens, you know, it's just an exam. Tons of people do lots of things in their life having not passed their exams, or pass their exams and then change their minds and done something different. You've got plenty of time, and don't worry about it. It's going to be okay. And if you need any advice, the next couple of weeks might be a bit mad, but I am around and I will be around in August. So I'm happy to answer questions. So good luck.